Okay, welcome back after lunch. So we'll have Loganayagam from ICTS talk to us about radiation reaction.
We can start. Yeah. Okay. Hello everyone. So today I wanted to talk to you in next 40 minutes about some work that I've been doing with one of my graduate students here at ICTS, Onkar, who is here. Okay, and a paper we had put out last year, and some set of works that we are doing it and so on. So as the title says, this is about radiation reaction and static patch holography and about de Sitter and so on. Okay, so let me start. Okay, so the question I wanted to ask, is in the context of de Sitter holography. So the paradigmatic example of holography that all of us know and love is an ADS5 cross S5. Okay, it is in an ADS spacetime, asymptotically ADS spacetime, and we have this map between type 2b string theory in ADS5 and n equal to 4 super angles on its boundary, kind of. Okay. So the question I wanted to ask was, are there similar examples for de Sitter? This is something that many people have asked since since ADS-CFT itself was discovered. But I think some of the things that I wanted to say today are new and hopefully interesting. Okay, so one of the things that motivated us to kind of think about this is some kind of a disquiet I have about these current proposals of de Sitter holography. I feel that they are very much focused on some very formal things about formal structures and so on, and formal analogies with ADS. And I wanted to see whether there's some kind of a physical problem which you would study even if you are not interested in holography. Okay, and something you can see about that physical problem and which kind of naturally has holographic features in it. Okay, so that is so many things that I'm going to talk about the problem itself is kind of independently interesting, even if you're not holographically inclined. Okay, but I think it has some holographic features which makes it interesting both at the formal level and so on. So with that very broad thing, so let me talk about some particular class of things in ADS-CFT, okay, which kind of is a somewhat of a inspiration for what we are going to say in de Sitter. Okay, so this is like it's like a kind of a very quick overview of something called as the fluid gravity correspondence. Okay, so fluid gravity correspondence is a particular restriction of ADS-CFT that I mentioned in last slide. Okay, to a subsystem. So what you do on type 2b side is that you look at a large black hole, okay, large in cosmological units, and you look at the lowest quasi-normal mode of this large black hole, and you just try to kind of ignore everything else. Okay, just the lowest quasi-normal mode. And on the other hand, like on the superangular side, you think of, so if you have a large black hole, you're thinking about a thermal state, a high temperature thermal state of n equal to 4 superangles. Basically a quark-gluon plasma, the analog of quark-gluon plasma for the gauge theory. Okay, and looking at the lowest quasi-normal mode is basically equivalent to looking at just the hydrodynamic modes of that quark-gluon plasma, and just forgetting about all the other intricate details, just thinking about it as a fluid which is flowing with some velocity, temperature, and forgetting about all the other things. The interesting thing here is that that you're basically reducing holography to a very small set of degrees of freedom on either side. Okay, and these degrees of freedom are open in the sense that if you put some energy into these modes, either the hydrodynamic modes on the gauge theory side or the lowest quasi-normal mode, eventually they kind of give out that energy to other things, right? The quasi-normal mode dies off in the black hole, whereas the hydrodynamic mode dissipates due to viscosity and things like that. Okay, so the point here is that the holography can be restricted to this small subset and can be understood. And one question we wanted to ask was that whether there is an analog of this kind of a restriction, this kind of a simplification, okay, for de Sitter. Of course, not clear because there's a kind of full-fledged duality which you can restrict and so on. But like here we do not have a duality. We don't even know whether there is a duality, okay, of any kind, okay. And so it's not clear, like whether what one can do, okay. But but one can take inspiration from history in the sense that like there is a very crude version of this fluid gravity correspondence which people kind of thought about even before like ADS-CFT and so on and so forth, okay, which goes by the name of membrane paradigm, which try to think about like a horizon in terms of a fluid and so on, okay. So this membrane paradigm, of course, had many problems, okay. One of the main problems was this decoupling problem, which is that like how do you decouple the near horizon modes, in any sense, okay. And as we know, like one of the greatest things about ADS-CFT and the Maldacena paper, which started all these things, is that like it solved the decoupling problem, okay. That by looking at ADS and so on and so forth. So there are some similar kind of decoupling problems in the case of de-Sitter also. It's not clear how do you get a decoupled sector. Okay, but like what I'm going to say is going to be at the same spirit as these membrane paradigm kind of stories. It has these, it has similar problems, but it has some interesting things. But I think like the moral is that like if you don't know anything, okay, maybe you can just start off with somewhere there, okay, and hope that you can try to make that precise, okay, and get somewhere, okay. So that's going to be the thing. So the idea here is to kind of look at some kind of a simplified open system, okay, in the case of de-Sitter, okay. And what I want to argue in the rest of the time I have is that like the system is to consider the problem of what I call de-Sitter radiation reaction, okay. So radiation reaction, let me remind you, okay, is a classic problem in classical electrodynamics, where if you have, say, a charge, okay, and if you have a charge which is moving in some random way, it's not moving with a constant velocity, then it kind of radiates, it loses energy and momentum, and it feels a force basically, okay, and which kind of takes away its energy and momentum. From it, there's a back reaction on the charge, okay. In some sense, the charge acts on itself, okay, so to speak. And then like and this is a very classic problem, and it is a problem which has especially received a lot of attention recently, okay, since the discovery of gravitational waves, okay, in LIGO and so on, because the gravitational radiation reaction problem is very interesting and very relevant for a lot of systems, like during the inspiral stage and so on. And it will probably become more relevant, like as we go into next generation of observations and things like that, where we have continuous gravitational waves and things like that. Okay, so the radiation reaction problem is very interesting, okay, and there's a lot of interesting things happening there, like which is inspired by this gravitational wave discovery. But that is the problem, and what I want to kind of argue, okay, is that it is a kind of a toy model which is at the same level, okay, where you can kind of try to see that there are some holographic features. So the main message of this talk is what I have highlighted here, which I want you to take home, is that like the radiation reaction problem itself has various holographic features, okay, and so the basic framework of holography I use, okay, so the various kind of proposals of various kinds, like about de-Sitter holography. The thing that I use is sometimes called as a solipsistic or a static patch holography, okay. So these are the references. I think the name itself is, as far as I know, due to Aninas, Hotnall, and Hoffman, okay, in this paper about more than a decade ago, okay. And then there are various other papers, like which are kind of, like related, okay. Some of the things I'm going to say about radiation reaction, okay, kind of were said by Goldberger and Rothstein, okay, in a paper, with a very classic paper in this field in radiation reaction. Many people who are working in this, that they know, it's a it's a very interesting paper, okay, but they kind of say something like this is like ADS-CFT and so on. This is a post ADS-CFT paper, okay. So some of the things that I'm saying, but we have various new things to say, And also, like this idea that there is an observer in de Sitter and you try to kind of encode things, okay, has also been said by these authors, like in various ways. So, like I won't be reviewing any of these things since there are various things that we want to say, which are kind of very distinct. But I think, like at a very rough level, at a kind of rough kind of inspirational level, I think this is roughly consistent with what these people say. But okay, so let me kind of say what the idea is. Okay, so the idea is as follows. So basically, you have you consider de Sitter universe, and the idea is that all dynamics in the de Sitter universe is kind of like a holographic rewriting, okay, of some quantum degrees of freedom of a single observer. So the idea is that there's a kind of a single quantum mechanical system, okay, which kind of if you kind of rewrite some internal degrees of freedom of that quantum mechanical system, the naive degrees of freedom of the observer emerge as the rest, and then the internal degrees of freedom become the rest of the universe. Okay, so that's a kind of rough idea. Okay, I'll try to kind of make this a bit more precise, but that is the rough idea. Okay, this is called solipsism, I think, because like there's a kind of a solitary lone observer, and from some philosophical things and so on. But the point here is that like that the idea here is that there is basically one quantum mechanical system which you're rewriting, like leaving out some degrees of freedom which become the naive degrees of freedom of the observer, and all the internal degrees of freedom become the rest of the universe. There's a possibility that like maybe this is what underlies like why we see very small anisotropies in CMB. I find it very interesting that maybe possibly like we see very small anisotropies because you're just starting with some quantum mechanical system and you're kind of rewriting, okay, and there are only so many degrees of freedom, and you don't have like enough degrees of freedom to have any more anisotropy than that. Okay, this is like very similar to like how people have made similar arguments for black holes and so on and so forth, black hole complementarity and various things that we have been hearing about. Okay, there's also this idea of static patch complementarity. I don't know who is the first person to say it, maybe Tom Banks, but the idea is that like there's like black hole complementarity, that internal degrees of freedom of the observer are rewriting even the modes which are outside the horizon and so on. Okay, so at least within the static patch, there's some of these one-Neumann algebra papers that I was citing, like seem to say that at least within the static patch observables, okay, there's a sense in which, like some kind of a tube around the observer, okay, has as much information as the static patch. Okay, so that is, yeah.
Do people moving around in this de Sitter see the observer, see this guy who has these large number of degrees of freedom as a wall or something?
Sorry, so there are other observers in the universe?
Us, let's say us. Let's say we are not the people who have these large number of degrees of freedom. We've been created by these large number of degrees of freedom. Now we're moving around this de Sitter.
So we are part of that large number of degrees of freedom.
We're part of those large. Now, do we see this observer as a kind of wall? He's located somewhere in de Sitter, right? So yeah. Would we go and be able to meet our creator? And
Well, I think that the point is there's no creator. There's only one. Like I think the point. Okay, I don't want to kind of go into like what it is. It's not as well defined as that to answer these questions. Okay, like all de Sitter things are. Okay, and maybe yeah. Anyway, but I think okay. The way at least I might think about it is that it's very similar to like how. You might, if you want to shift from one observer to another observer, you might just want to rewrite things of what you're integrating out and what you're not. Okay, so that's how I would think about it. There's one set of degrees of freedom. Okay, and in some sense, by kind of centering your attention on one observer, you're saying that okay, I'm going to keep them and kind of rewrite the rest of it as the universe. Okay, and all the other observers. But if you want to go to the other observer, you just kind of do it for a different set of degrees of freedom within this thing.
Just one last. Yeah. Does this observer carries a large number of degrees of freedom? He has a large computer surrounded by maybe a black hole. Must be.
The observer carries a large number of degrees of freedom in the quantum mechanical description. Okay, the observer.
But he doesn't carry these large number of degrees of
freedom in the gravitational description
in space-time.
No, because in some sense those degrees of freedom are kind of spent in rewriting the space-time.
But then why is he there at all in the space-time? I mean, ADS...
Because some of it is not rewritten. Okay. I mean, I do not know. But I think, yeah, but that's a kind of rough idea of this thing. So I think,
Sorry, can I just say something, Lucas?
Yeah.
Sorry, first of all, I know this is probably tangential to your talk because I've heard some of it before I'm here. Hi, yeah. So, but there are two different pictures here. One of them is the idea which I agree with, that maybe you can rewrite everything as on a codimension 2 surface on the late time boundary, which would be some way of saying your solipsistic holography, which I would agree with.
This is more like a time-like cube.
I know, but I would agree at least that on a late time slice, if you took a codimension 1 part of the late time slice, you'd be able to find a dual description. But the idea of the observer that you have in the von Neumann algebra analysis, that's different. That observer just needs to carry more energy or more entropy, a lot of entropy. So, and not back react much. So that's like an amoeba, much less than Planck scale, much larger than cosmological scale. That's all and in fact, that's all you need for your description of radiation reaction, right? So an amoeba or a virus is good for you as an observer. Yeah,
I think, so the thing that I'm going to talk about is a very small part of it. Okay, so it doesn't need, you can even forget about all the holographic part of it. Okay, but I think, the question is that, maybe let me put it this way. The thing is that what can be the only reason I'm talking about these things, okay, is that, whether these things can tell us something useful about how you should think about radiation reaction, okay, and I feel that it does, in the sense that, this holographic features that I'm going to talk about is somewhat inspired by trying to see whether you can kind of think about the radiation reaction problem in this language, okay. And so that's all the kind of use of these stuff, okay, at some level for me. But I think, yeah. So there is a problem which is related to these questions that are being asked, which is the question of decoupling, right? It's the thing that I was saying, okay, which was the problem with holography even before, before, Maldaceno's paper and so on, which is that, when you have something, okay, and you're thinking about something rewriting and so on and so forth, okay, how do you kind of think about that as a separate degree of freedom, or how to freeze things there and so on and so forth, okay? And it's not at all clear for the observer, okay? And then you have to play these games of, okay, the observer should be heavy enough not to be, kicked around too much, but not too heavy to kind of modify too much, and these kind of things. So these are all, these statements are, I think, various efforts to try to kind of solve the decoupling problem. As I see, the problem remains, okay? I don't think it is really solved, okay? And that's there, okay? So that is the fly in the ointment, so to speak, of this whole business, and it is there, and the decoupling problem will be there, okay? But the point is that, what can we say about it, okay? I'll say something about, what you can decouple and what you cannot, and what you fix and what you don't fix, and so on, okay? So that is a basic point. Yeah, so they're all very vague, okay? And in particular, what I want to kind of do is to kind of try to see, by thinking about the radiation reaction problem, whether we can get something like a GKPW prescription, which is that, so GKPW prescription in ADS-CFT is the statement that you fix certain things, you fix the non-normalizable modes, okay? And then you kind of, those are the boundary conditions, those act as CFT sources, and then you kind of solve for the normalizable modes. So normalizable modes are some kind of states, and they are dynamical, okay, they are not fixed, okay? And the question is that, how do you kind of freeze some things and then let other things be dynamical, okay? Because when we're talking about observer in some universe like DCITR, okay, or in anything which is in the middle of the universe, okay, obviously the observer is cannot just freeze, the observer cannot choose whatever energy to have, okay, because it's a Hamiltonian constraint and so on, okay, and there are many other things. The observer doesn't have as much freedom as an observer who is sitting far away in some asymptotia, okay, and it's not clear how do you kind of think about it, okay. But what I want to say is that the radiation reaction problem is somewhat similar. So the radiation reaction problem, as I was saying, is this question where you say, okay, you have a charge, okay, the charge is talking to electromagnetic fields, but let's say for a moment that the charge is moving in some particular way, okay, let's say it's going around in a synchrotron or something, okay. So you're giving it some kind of a trajectory, okay, which is maintained by something, okay? And the point here is that, like then you are asking how much energy and momentum it is losing, right? So that's a typical standard radiation reaction problem. And of course, this is it's a limited in the sense that, like, and similarly, you can kind of say in gravity that, okay, there are binary system which is moving in a certain way, you can ask how much gravitational wave it is sending out, okay? And of course, like you can't kind of specify this very independently, because at some point you have to kind of come back and consistently solve the Einstein equations, okay? And that's a problem. So it's not quite decoupled as we would think. But the question is that, like how do we think about, okay, what you fix and what you what you kind of let vary, okay? And what I'm trying to say is that that problem is very similar to the de Sitter radiation reaction problem, and you can actually give something like a GKPW prescription for solving that problem, for the radiation reaction problem. Okay, so that is going to be the basic idea, okay, that I want to say. Yeah, so this is a kind of a basic picture, okay, which I think I have said various things about. So the idea here is that, like, so there's one picture where you have one big quantum mechanical system, okay, out of which there's some small degrees of freedom, which I call the naive degrees of freedom of the observer, which we think of as the observer degree of freedom in the gravitational description. And there are some internal degrees of freedom. And then, like you kind of rewrite it, and these naive degrees of freedom of the observer are open, okay, in the sense that they lose energy to their surroundings and to the rest of the universe, okay, and like the same way hydrodynamic modes in the coagulon plasma do, okay, and the idea is that, like there is a corresponding thing, okay, on the other side, okay, which is like, like you have the open quantum mechanical thing, in the gravitational description, where which describes the radiation reaction. And the statement is that in some sense the effective theory of the naive degrees of freedom, okay, if you think of the naive degrees of freedom as the hydro degrees of freedom, okay, then you have the the dynamics is as the radiation reaction dynamics, okay, which you can kind of derive from the de Sitter side, okay. So that is the basic picture, okay. So let me just come to this statement about like GKPW and so on. So this is what I was.
Sorry. What is FGC? I've been seeing it on many slides and I don't know.
Sorry, this fluid gravity correspondence. Sorry, I just want. I was just lazy. Okay, I was just lazy. So it's just fluid gravity correspondence. Doesn't matter. Yeah. But yeah, sorry for that. Yeah. Anyway, so the point here is that like. So the point here is to kind of understand in the radiation reaction problem, how do you think about the analog of normalizable modes and non-normalizable modes? So the non-normalizable modes and normalizable modes I had already talked about. Okay, this is what you do in ADS. Okay, basically where you fix like some non-normalizable modes. Maybe it's the metric seen by the fluid and so on. Okay, the CFT sources. Okay, and then like maybe the background electric fields, non-dynamical electric fields. Okay, that coagulon plasma sees. And then, like you solve for the normalizable modes, which corresponds to the fluid state, and you kind of derive the effective theory for the normalizable modes, which is the fluid dynamical theory, okay. Now the point here is that, so what I'm trying to say is that, in de Sitter, you do something similar, okay. So if you have, I'll kind of show explicit equations, okay, for Maxwell theory in de Sitter, okay, how this works. But the general idea is basically clear that if you kind of solve, okay, if you have a point like observer, okay, it's probably a point like charge, okay, and if you solve Maxwell equations, you have modes which are blowing up, things like which go like, let's say 1 by r to the power L plus 1 in the electrostatics, and things which go like r to the power L, okay, things which are regular, okay. So this is what you get, okay, and this is what you usually get when you solve for, like wave equations, that you have modes which kind of blow up, okay, which are kind of basically Green's functions, okay, at that with a delta function source at that observer, and then there are kind of just normalizable solutions, the things which are just regular, okay, and so the point here is to kind of try to fix these field modes which blow up, okay, and kind of interpret the coefficients there, okay, as the time-dependent multipole moments of the observer. Okay, so which you can do, I'll show you explicitly how you do it. So you have these electric multipole moments and magnetic multipole moments, which you can kind of read off from the field modes, which kind of blow up at the observer, and you kind of remove some power of art and get that, okay? And then you can look at the corresponding modes, okay, which are regular there, okay? So the idea here is that, let's say in de-Sitter, you kind of also impose some boundary conditions. So this is what we do in anti-de-Sitter also, where you kind of fix the non-normalizable modes, okay? And then you have some boundary condition in IR, maybe some ingoing boundary condition if there's a black hole and so on, okay? And then you ask, like what is the normalizable mode? And then reading of the normalizable mode is the web in the CFT, which is given in terms of the source, okay? So you get the Green's function, the 2-point function, the CFT 2-point function that way. So the idea here is that is very similar, where you kind of fix the field modes, okay, which are blow up at the observer, okay? And in terms of that, you look at the subdominant modes, which are regular. And the idea is that regular modes, okay, with some boundary conditions, okay, let's say some outgoing boundary conditions at the de-Sitter horizon, as it will be, okay, then that coefficient basically gives you the radiation reaction, okay. So that is the basic idea, okay. So now let me kind of say some of these things in equations, okay. So let's kind of look at this thing. So we have an outgoing static coordinate system, okay, around some observer who is taken to be at r equal to 0, okay, and you have so this d omega d minus 1. So I mean d-Sitter d plus 1, and there's a sphere d minus 1 around the observer, okay, and the point here is that we are trying to solve this problem. So this is a very standard problem, okay. You can solve this problem, and the idea is that you can take the simple model where the observer is just a particle with some time varying electric and magnetic moments, okay. It can be dipole moment, quadrupole moment, something. The charge should be conserved, but because of the Gauss law, but all the other moments, okay, can be time varying, okay, in general, okay. So you can have, this is like a standard, like a Griffiths level problem or something, about a dipole sitting and changing in time, okay. But now in de-Sitter instead of in flat space. So that's all the difference, okay. Then what you can do is that you can solve this problem by basically taking the Maxwell equations and expanding all the electromagnetic field strengths, okay, electric fields and magnetic fields, in terms of spherical harmonics, which is a good thing to do because this geometry has spherical symmetry, and you can also go to frequency domain because it has a time translation symmetry within the static patch, okay. So this is my kind of this thing. So these are the the scalar spherical harmonics, and those are the vector spherical harmonics. Here I denote the sphere indices, okay. So basically, so that will be my this thing. So you can do this. So this is a long equation, probably the longest equation in my talk. But the idea here is very simple. So you just take the F mu news, okay, and you just expand it, okay. You should expand it in derivatives of scalar spherical harmonics and vectors and vector spherical harmonics and derivatives of vector spherical harmonics. So these are all the more general things that you can do, okay. And we are doing it in the frequency domain, okay, the frequency of the outgoing time. And then you just these coefficients which occur here, okay, are various things. So my notation here is basically that you have a subscript S, okay, if it corresponds to scalar spherical harmonics, a subscript V if it corresponds to vector spherical harmonics. If you have two vector indices, you have a VV and so on and so forth, okay. So but it's just something. So you can just take this ansatz, okay, which is a more general thing you can do, and just feed it into the de-Sitter Maxwell equations in the de-Sitter background, okay, and solve it. So I won't kind of go through that, okay, but that's all standard stuff, okay. But I just want to kind of show you what comes out, if you just solve it in the standard base, okay. So let's kind of look at a very specific kind of modes, okay. So you have this ES, okay, which is basically this FIU, okay, which is like the electric field along the sphere, okay. It's like the surface electric field, okay, and then ER, which is a radial electric field, okay, and then HS, which is some scalar mode, okay. So all these are things which multiply the scalar spherical harmonics, and what I'm looking at is the small r behavior of the solutions, okay. So the small r behavior, okay, is actually same as flat space. Actually, this if you just did the Minkowski analysis, as you would expect, like at small r, the cosmological constant and all that doesn't matter, okay. So the small r behavior doesn't have any h, and it can be, it's just what you would get if you just did Maxwell theory in Minkowski spacetime of d plus 1 spacetime dimensions, okay. And what you get is that you get various r powers, and the coefficients are all the same, okay. And this JE is analog of the electric multipole moment, okay. It's kind of related up to some factors to what Jackson defines as electric multiple moment, spherical electric multiple moment in 4D, okay, in 3+1D in his book, okay. But the point is that, you know, like, so you get these, okay. So the point here is that, you know, like, so you get three kinds of behavior, okay. So you get something which goes like J, and then you get something which goes like L into J, okay. And then something which goes like I omega J, which means that, you know, like this guy, the last guy is 0 if you just have a multiple moment which didn't change with time, okay. So the point here is that, so what you want to do is to kind of fix JE, okay, and calculate this thing. So this is similar to, you know, like how we will do this in ADS, okay. So the statement is that I fix JE by looking at this ES component, okay, the surface electric field, and taking a r going to 0 limit of that, multiplying by some r. Whereas, you know, like I use the radial electric field. So the radial electric field has some behavior which goes like that. So you put some counter terms to, you know, kind of remove this leading behavior, and you kind of dig out the subleading behavior out of this ER, okay. And if you do that, okay, and this counter term, by the way, is a function just of ES. See, that's what we would usually do in ADS, where, you know, like we think of the counter terms as just made of non-normalizable modes. Okay, so you just kind of add various powers of r times ES here, okay, and omega and so on and so forth, in such a way that, you know, like this guy is finite. And when you do that, okay, what you get here is JE times some KE, okay, and the KE is basically the radiation reaction. So this is kind of exactly analogous to ADS. In fact, you know, like you can even kind of map various things to just ADS by, you know, like looking at some analytic continuation or something. But the point here is that this KE, okay, has the physical information of what happens if you have a multiple moment, an electric multiple moment, let's say a dipole moment, which is changing with time, okay, and what is the radiation reaction on that multiple moment? What is the electric field that you know, like you get there, okay? So I want to kind of emphasize that this is exactly what we would do in ADS, in the sense that the radial electric field, remember, if you have a black hole, and the radial electric field actually has the information about the charge of the black hole and so on, okay, so which is what we will consider as the state information, okay, and then any kind of tangential electric field is what we would call as the non-normalizable mode information, which you turn on for the CFT, the sources that are turned on for the CFT, and it is exactly the same thing. Okay, so this kind of, you know, like one can then check that KE, if you take the flat space limit, if you take, you know, like H going to 0 limit, it actually reproduces all the radiation reaction for various dipole moments and quadrupole moments and so on and so forth. Okay, so this is actually the correct thing to do because it gives you the correct answer. Okay, first of all, the second thing is that it's also very similar to what we would do in ADS. But you can ask, what does this mean? Okay, so what does this, you know, like, you know, it's actually interesting to ask, you know, like what this means and what this description means, okay, and what we are considering as the non-normalizable mode, as a source, and what we are considering as a web, because not already, you know, it's not as clear as in the ADS problem, okay, because everything is seems coupled and so on and so forth, okay. So here I have a picture, okay, which kind of, you know, tells you what happens, okay. So let's say, you know, like you have, you kind of just blow up this observer into a spherical shell, okay. Then there are kind of two kinds of electric fields, right? You know, like, so we know from basic electrodynamics that, you know, the radial electric field jumps, okay, as you kind of cross, you know, like some charged shell, okay. And that is the kind of thing that you kind of think of as the normalizable mode, okay. Whereas, you know, like the thing that doesn't jump, okay, the thing that is supposed to be continuous in the standard electrodynamics, is what we are treating as a non-normalizable mode. So in some sense, you can think of it as, you know, like you're kind of integrating over the shells appearing and disappearing. Okay, so that kind of changes certain electric fields, doesn't change certain other electric fields, and the electric field that doesn't change, okay, is the non-normalizable mode in some sense that you keep fixed. And the things that change as you know, like charge shells fluctuate in and out of the state, in some sense, you know, like are things that you kind of, you know, let it fluctuate, let it kind of evolve. You know, like in terms of these continuous fields. There's actually, this picture also continues to hold true, okay, when you go to the magnetic things, so, you know, where you have magnetic multiple moments. I will not bore you with this, but this also, you know, like very standard, you know, like you know, very flat space behavior. So you have, you know, like a certain H field, which exactly you can go and check, that is a H field which we will say is continuous, which we think of it as a non-normalizable mode, okay, which we fix, and the H field that can jump around if you put a current shell or something, okay, which we kind of think about it as a normalizable mode, and you can add counter terms like to the non-nominal mode in terms of the non-nominal mode and get, like the standard formulae for the magnetic radiation reaction. Okay. Okay. So now, like you might say that that what I have kind of described is not quite GKPW, okay, because sometimes people distinguish between these extrapolate dictionary versus differentiate dictionary, where the extrapolate is where you have fields and you take these limits, like the kind of thing that I was showing you, okay, whereas like differentiate is you kind of calculate some path integral with some sources and you kind of differentiate with respect to the sources to get these things, okay. Now, like these are supposed to be equivalent in ADS, CFT and so on, which I will not go into, but you can this thing. But there are kind of issues, like in DCTR where these dictionaries are not quite always equivalent. Okay, like I will not at least in this future time slice kind of things that Suvrat, Sandip, and so on talk about. Okay, so the question here is, like I think part of the thing is to kind of get a path integral where you can fix some sources, and part of it is decoupling. Okay. And about composite operator renormalization and so on and so forth, which these guys talk about. Okay, and the question is that like so it's an interesting question to ask that. Okay, so I have given some kind of extrapolation, okay, of fields with counter terms and so on to get the radiation reaction, but can I get it from the path integrals? So the answer is actually yes, but I won't kind of have time to describe it in detail. Okay, but I will refer you to this this paper that I had referred to in the beginning. Okay, the idea, but let me just say some very vague words. The statement is that like you can actually write on a path integral over some geometry, which is like analog of a real-time analog of Gibbons-Hawking geometry. It's also similar to various geometries that I, Mukund, and various people have studied. Like in the context of various black holes. So there are various similarities to various things that there are this thing, but the point is that you can actually write down a path integral, okay, and you can show that you can add local counter terms and you can evaluate the path integral in terms of the sources, and it gives you some kind of an effective action, okay, and that effective action is some for those of you know it's a Feynman non-influence functional of the observer, which you can derive from actually doing this kind of path integral in very GKPW kind of way. Okay, and you can actually like differentiate with respect to sources and get these formulae that I was telling you about. This kind of extrapolate kind of formulae can be derived, okay, starting from a path integral with counter terms and making it finite and showing that those counter terms just work for these cases also. Okay, so there's a question of like, so we haven't so this is mostly like linearized analysis, all of it, like we haven't done interactions in the DCTR case, okay, which is kind of crucial to try to see whether you will still get like local counter terms and so on and so forth, like to as you include interactions. But I think like there is enough evidence, like people have been doing radiation reaction computations, following this Goldberger-Rothstein kind of way, where you have a Berlin effective field theory and putting counter terms there and getting things. Those are all in flat space. But I think like those kind of calculations and the success of those calculations kind of lead us to believe that if we did this, like we should be able to do it here also. Okay, that we should be able to do local counter terms even when we include interactions, but of course it has to be done and so on. So anyway, so let me kind of say one more thing and then conclude, which is something I wanted to say, which is that like I mean, even if you don't like you are not interested in any of this holographic thing, okay, radiation reaction is an interesting problem in itself, as I was saying, and radiation reaction in curved spacetimes is an interesting problem because of these gravitational wave kind of questions. And at some level, DCTR, I want to advertise, is the best curved spacetime you can do this computation on, because it's a very nice spacetime where you can write the Green's functions, everything, this thing, and you can kind of solve it, and you can see a lot of things that people say about more general curved spacetimes, okay, and what happens there, okay. And what you get is that, like if you... The radiation reaction, in some extent, is better controlled than flat space in the sense that for long times, okay, because in some sense, DCTR kind of, there's some memory terms and so on, which are kind of, like dispersed away by the expansion of the universe, I think, okay. We already see some of that in our, this thing, but I can tell you more about it. Sorry, I didn't have much time to talk about this, okay, but I can tell you more if you just catch me after the talk, okay, after in the tea break or something. The point here I wanted to just tell you is that this is some formula, okay, of radiation reaction of charges, electromagnetic fields, of moving charges, okay. This is just the usual ALD formula, okay, which is A dot. Okay, and then there's a in 5 dimensions also there's a formula, but the important thing here is that this is a completely covariant formula. This is a covariant formula in the sense that this is all these covariant, this d by d tau is all like de Sitter, proper time and so on and so forth. This is charge moving, and you can actually write down some very close form expressions. Okay, you can see many such formulae in our papers. Okay, and there are a lot of interesting structures of how they arrange themselves and so on, and they're very heavily constrained. This is what we see. These numbers are all very strongly constrained. Okay, by various consistency conditions. But okay. So since I'm kind of run out of time, okay. So let me just conclude. Okay. So basically, what is the summary is that we have a very GKPW-like proposal for de Sitter and radiation reaction in particular, and the CFT correlation function, which is the usual thing that we compute, are replaced here by radiation reaction physics of how moments a radiation reaction is and various things about radiation reaction. We have done it for scalars and in the paper, and I showed you some of the results that we have for electromagnetism. There's a question of including gravity, including interactions, and so on and so forth. Okay, there's and then there are many other things one can ask. But I think, just to say that, there are many other interesting things other than just the holographic motivations. So one of the things that I think is interesting is that whether there's actually a real system, okay, in cosmology, where you can actually measure the cosmological radiation reaction. That is radiation reaction, which kind of includes the effects of cosmological constant. Okay, so you need to look at big enough systems and so on. Okay, so that's an interesting question on itself. Anyway, let me conclude and thank you. Okay.
We can have a couple of questions.
Okay, let me try to paraphrase, perhaps wrongly, your starting point. Is it roughly something like this? Take the static patch of de Sitter and take the geodesic at the center of de Sitter. Now, is your idea that there is a hologram for the static patch roughly at the center or corresponding to the observer at the center?
Yeah, you can put a time-like tube around
a time-like tube along it. Yeah. And maybe the number of degrees of freedom in this quantum mechanical theory equals, say, the de Sitter entropy. And you can and what you're giving here is the map, in a sense, of the normalizable and non-normalizable modes for that time-like tube.
Yeah.
Is that roughly?
Yeah. By kind of imposing the physical and I think very sensible statement that after you put these boundary conditions and solve for it, the answer should be radiation reaction. See, the point is that, what is it computing? Okay, right? In ADS-CFT, this is computing the CFT correlation function. Those are the observables, so to speak. Okay. So the question is, it's not obviously clear what is the thing, but I think a very, physical observable is just the radiation reaction felt by an observer in that. And then you can just ask, okay, so I want to put whatever boundary condition, whatever formal thing I'm doing, it should give me that. Okay, it should reduce to calculate that calculation. Okay, and that kind of naturally gives these things. Okay, but there's also this path integral way of thinking about it and so on, which also gives the same thing. Yeah.
In ADS-CFT, there is like holography and the time-like tube theorem. And these are two very different things, right? Because the time-like tube does not give you locality on the boundary. For that, you need gravity. And this is also seen in the fact that time-like tube is a statement about QFT, not about gravity. So you're talking about holography, but it looked like you were just using QFT things or something like time-like tube or something. Where does actual holography come in here?
In the sense that, the boundary conditions that you impose are a bit like GKPW. That is all there is.
Yeah, I think that's consistent with time-like tube, right?
Yeah, I agree with Ronak. Right? GKPW is not, although we say it's holography, it's not really holography. It would work in quantum field theory without gravity. Because all it's saying is, you give me some boundary conditions and I solve partial differential equations. So you could do it with a scalar.
I don't think it is just solving the partial differential equations. It's about, see, when you do counter terms, it's a question of what kind of counter terms are allowed, right? And what you keep fixed and what you don't keep fixed, right? Okay, see, you can solve via various kind of boundary conditions, okay? But the point here is that, there's I think, yeah, at least I have not seen time-like tube theorem being phrased in terms of GKPW. Let me put it that way.
Isn't it clear? You just give me a time interval of length pi in empty ADS or a time interval of all time.
It is true, as we have shown, okay?
No, but isn't it clear in ADS also? You give me the boundary and I can deform the boundary. It's just the causal diamond in the boundary, right? So it's like.
Sure. I think it works. Yeah. We are not arguing about that.
PW is literally the equivalence of extrapolate and differentiate dictionaries.
Yeah, which is not obvious in DCITR. There
Yeah.
are arguments that doesn't work in DCITR. Yeah.
Okay.
Okay. So, and especially here, I mean, you know, you are in the middle of the geometry, which is very different than, you know, like when you are far away. Okay. It's not like clear that there's even something to, see, it's not even clear that there's something to compute, I think, in a priori. Okay. But what I'm trying to say that at least in some sense there is something. Okay. Even in a gravitational theory. Okay. You can have a binary and it might lose things by a radiation reaction. That's a completely physical thing to ask. Okay. Maybe I do not know how to kind of define it in a non-perturbative way, but that's completely something that, you know, like which is experimentally observable, and it is it's kind of experimentally observed. Okay, in the sense that we are living in an FRW and we are kind of running LIGO. Okay, so yeah.
Okay, due to lack of time, we'll take questions later during coffee break. Let's thank Loga again for a fantastic.